The Airbus A380 weighs 575 metric tons at takeoff. That's 1.27 million pounds of metal, fuel, and 600 passengers, somehow rising into the sky at 170 knots and climbing to 39,000 feet. Common sense says it should be pinned to the Earth. Physics says otherwise. But here's the part nobody tells you. The reason your science teacher gave you for how a wing creates lift is wrong. Not slightly wrong, fundamentally wrong. And at 575 tons, that mistake is the difference between flying and falling. Today, we're going inside the 4 engineering systems that keep the world's heaviest passenger jet in the air. Once you finish this video, I promise you'll never look at a takeoff the same way again. In 1903, the Wright brothers flew 120 feet in 12 seconds. The aircraft weighed 605 pounds. Since then, the entire story of aviation has been about one engineering question. How big can we make this thing before physics says no? The Boeing 747 answered that question for almost 3 decades. 4 engines, a double-deck nose, capable of carrying 400 passengers across an ocean. Then, in 1988, inside Airbus's engineering campus in Toulouse, a man named Jean Roeder started running secret feasibility studies. He wasn't trying to build a better 747, he was trying to build something Boeing couldn't. The plan was audacious, an aircraft with 2 full passenger decks running the entire length of the fuselage. Maximum takeoff weight, 575 tons. Wingspan so wide it would force every major airport in the world to rebuild its gates. Airbus went public with the idea at the Farnborough Air Show in 1990. By December 2000, the Airbus board voted 9.5 billion euros to build it. The aircraft was renamed A380. On April 27, 2005, registration FWWOW lifted off from Toulouse-Blagnac. 2 captains in the cockpit, Jacques Rosay and Claude Lelay. They flew for 3 hours and 54 minutes. When Rosay landed, reporters asked him what flying a 575-ton aircraft felt like. He said it felt like handling a bicycle. For anyone who had spent 5 years calculating whether this could even be done, the precision of that understatement was its own kind of engineering poetry. But how do you actually make a building-sized aircraft handle like a bicycle? That's a question with 4 answers. Let's start with the part everyone gets wrong. If you've ever taken a high school physics class, you've seen this diagram. The wing has a curved top and a flatter bottom. Air flowing over the top has to travel farther than air flowing underneath, so it moves faster. Faster moving air has lower pressure. Lower pressure on top means the wing gets pushed upward. Sounds clean. Sounds logical. It's also wrong. NASA has explicitly stated that this explanation, called the equal transit time theory, is incorrect as a complete description of lift. The 2 air streams don't actually meet at the trailing edge. The air over the top arrives there well before the air underneath. The theory falls apart the moment anyone measures it. So what is actually keeping a 575-ton aircraft in the sky? The real answer involves 2 physics principles working together. The first is what your textbook tried to teach you. There genuinely is lower pressure above the wing and higher pressure below it. That part is true. But the bigger story is what the wing does to the air it touches. When the A380's wing slices through the atmosphere, the tilted shape of that wing forces the entire column of air around it to deflect downward. Tons of air per second, pushed toward the ground. Every action has an equal and opposite reaction. The air gets pushed down, the wing gets pushed up. That's it. If you've ever held your hand flat out of a car window at 60 miles an hour, you already know how this works. Flat palm, almost no lift. Tilt the palm up slightly, and you feel the wind force your hand toward the sky. Engineers call that angle of attack, the angle between the wing and the oncoming air. It's the single biggest variable in whether a wing produces enough lift to fly. Now here's where things get interesting. The A380's wings have a total surface area of 845 square meters, nearly the size of 3 NBA basketball courts. At cruise, those wings are deflecting roughly 5.6 million newtons of force downward every second. That's the lift needed to support 575 tons. Every second, every wing, every flight. The physics gets written down as the lift equation. Lift equals 1/2 air density, times velocity squared, times wing area, times the lift coefficient. The two things engineers can change are wing area and the coefficient. The two things they can't are air density and your speed. And that's where the A380 has a problem. At 39,000 feet, the air is roughly 1/4 the density of the air at the runway. The engines are weaker up there. The wing produces less lift at the same speed. To compensate, the aircraft has to fly fast, around Mach 0.85, roughly 567 miles per hour. But fly too fast over a normal wing, and a different problem appears. Air flowing over the top accelerates so hard it goes supersonic. Shock waves form, drag spikes. The aircraft starts shaking itself apart. So Airbus engineered the wing to cheat physics. The A380's wing has what's called a supercritical airfoil. The top of the wing is flattened, almost level. This delays the moment when airflow over the top goes supersonic, letting the aircraft fly faster without paying the drag penalty. The wing is also swept back at 33.5 degrees, which buys it even more high-speed efficiency. But the supercritical airfoil has a cost. It's less efficient at low speed, which is why during takeoff and landing, the A380's wings transform. Slats extend from the leading edge, flaps extend from the trailing edge. The whole wing changes shape, growing larger, adding curvature, generating dramatically more lift at slower speeds, straight out of transformers. The landing speed is just 130 to 135 knots. Astonishingly slow for something this heavy. The takeoff run at full weight requires a runway just under 3,000 meters long, 3 kilometers of asphalt to accelerate 575 tons through air thick enough to lift it. And here's the number that should make you uncomfortable. Wing loading is the weight an aircraft places on each square meter of wing. The A380's is 680 kilograms per square meter. Every square meter of that wing is carrying the weight of a fully grown horse, per square meter, at 39,000 feet, but there's a limit to how hard you can push a wing. Angle it too high, and the smooth airflow on top separates from the surface. Lift collapses. The aircraft stalls. For the A380, that happens around 18 degrees of angle of attack, and at 575 tons, recovery from a stall isn't quick. So the wing is doing two impossible things at once. Generating enough force to hold the equivalent of 7,500 humans in the sky, and doing it without ever asking for more than physics will give. That's Act 1, the wing. But the wing is only useful if it's bolted to something that doesn't shake itself apart. If you watch an A380 wing during takeoff from the right seat angle, you can see something that looks like structural failure. The wingtip bends upward by as much as 4 meters. 4 meters. That's not a defect. That's the design. A rigid wing at this scale would crack under load. The bending forces at the wing root of an A380 at takeoff are equivalent to suspending 2 fully loaded Boeing 737s from each wingtip. During a 2.5 G turbulence event, multiply that by 2.5. The solution is engineered elasticity. The wings are designed to flex up under load, distributing stress like a bow being drawn back. If the engineers tried to fight that flex with extra structural mass, they'd add weight the aircraft can't afford. So the entire airframe is a precise recipe: 61% aluminum alloys, 22% advanced composites, 10% titanium and steel. The remaining 3% is a hybrid material called glare. Glare is fascinating. It alternates thin sheets of aluminum with layers of S2 glass fiber bonded in epoxy resin. It was developed at the Technical University of Delft in the Netherlands in the 1980s and patented in 1987. It's 25 to 30% lighter than pure aluminum at the same strength. And here's the part that matters at altitude. If a crack starts in one of the aluminum layers, It travels outward until it hits a glass fiber layer. Then it stops, dead. Each fiber layer is a built-in crack arrestor. Think of it like plywood. Layers alternating direction, so a flaw in one is contained by the next. The A380 was the first commercial aircraft to use glare in serious quantity. Upper fuselage panels, the same panels that have to survive 50,000 pressurization cycles over an airframe lifetime. Speaking of pressurization, at cruise, the cabin is pressurized to the equivalent of 5,000 feet. The outside air, at 39,000 feet, is pressurized to almost nothing. That differential pushes outward on every square inch of the hull with a total force equivalent to nearly 100,000 tons. The fuselage is constantly expanding and contracting, almost like it's breathing. Every flight cycle is one breath, tens of thousands of breaths over an aircraft's life. Running through this expanding, contracting structure is a hydraulic system operating at 5,000 pounds per square inch. More than double the pressure of standard commercial aircraft. Higher pressure means smaller pipes and lighter actuators. Every gram counts when you're carrying 575 tons. But here's the part of the structural story Airbus doesn't put in the brochure. On February 14, 2006, in a structural test facility in Toulouse, engineers were loading the A380's wings to destruction. Certification rules require commercial aircraft wings to survive 150% of the maximum expected in-flight load without failing. The hydraulic rams pushed the wingtips up and up and up. At 145% of limit load, the wings ruptured, both wings symmetrically, 3.3% short of the required mark. There was no disguising what that meant. An aircraft designed to carry up to 853 passengers had just failed its safety test on Valentine's Day. Airbus's spokeswoman called for what she described as refinements. The fix was 30 kilograms of stringer reinforcement strips added to every airframe. The certification went through, but the wing problems weren't over. 6 years later, in January 2012, Qantas mechanics inspecting an A380 found hairline cracks in something called wing rib foot brackets, small L-shaped fittings that connect wing ribs to skin panels. By February 8th, EASA had ordered inspections across the entire global fleet. The agency's spokesperson said inspectors were finding cracks in almost every plane they checked. The root cause was the alloy, a high-strength aluminium called 7449 used in the first 120 aircraft. It turned out to be too brittle for the complex stress cycles, where wing ribs meet wing skin. Airbus switched to alloy 7010 from aircraft 121 onward. Earlier airframes had their brackets replaced. The total repair cost across the fleet exceeded 500 million euros. So when you watch an A380's wings flex 4 meters at takeoff, you're not just watching engineered elasticity. You're watching a structure that broke during testing, was reinforced, broke again in service, was reinforced again, and is now flying. The aircraft you see in the air today is the survivor of 2 decades of structural learning. That's the body. Now, we need to talk about what makes it move. The A380 has 4 engines, either Rolls-Royce Trent 900s or Engine Alliance GP 7200s, depending on which airline ordered it. Combined maximum thrust, roughly 300,000 pounds of force. Here's the part most people miss about a modern jet engine. The combustion isn't doing most of the work. A turbofan engine at this scale is basically a giant fan attached to a small jet engine. The Trent 900 swallows roughly 1,200 kilograms of air every second. The vast majority of that air goes around the central combustion chamber, accelerated by a fan that's almost 3 meters wide. That bypassing air produces about 75% of the engine's total thrust. The hot core just powers the fan. Air goes in, gets compressed about 38 times by stages of compressor blades, mixed with fuel, ignited. The expanding gas drives turbines that spin the fan, which moves the bypass air. The remaining 25% of thrust comes from the hot exhaust shooting out the back. This is why bypass ratio matters so much. The Trent 900's bypass ratio is 8.5 to 1. For every kilogram of air through the hot core, 8.5 kilograms bypass it. Higher bypass means better fuel efficiency and quieter operation. Lufthansa's A380s produce half the noise of a Boeing 747-200 series, while carrying 160 more passengers. But efficiency at this scale is relative. The A380 burns 17.5 tons of jet fuel every hour at cruise, around 1 liter of fuel every fifth of a second per engine. A 14,800-kilometer flight can carry up to 253 tons of fuel, which means more than 44% of the aircraft's maximum takeoff weight is fuel. So when you board an A380 from Dubai to Los Angeles, almost half the aircraft you're sitting in is, by mass, kerosene. Now here's where engine design becomes a survival story. November 4th, 2010. Qantas Flight 32, Singapore to Sydney. Captain Richard de Crespigny is in command of an A380 carrying 469 people. 4 minutes after takeoff from Changi Airport, the number 2 engine, the left inboard Trent 900, explodes. Inside the engine, an oil feed pipe with a manufacturing defect had been weeping fluid into the bearing assembly. The resulting fire fractured the intermediate turbine drive arm. The turbine disc, freed from any load, spun up uncontrollably until it burst. Chunks of titanium disc punched out of the engine casing at roughly twice the speed of sound. Some of those chunks went through the left wing, severing more than 600 wires, puncturing fuel tanks, disabling hydraulic circuits, damaging landing gear controls. The flight deck filled with warning messages, more than 50 ECAM system alerts. Half the aircraft's redundancies were gone. Fuel was streaming from the wing. The aircraft was 50 tons over the certified maximum landing weight. De Crespigny had 4 other pilots on board that day. They worked through the alerts methodically for 55 minutes, identifying what worked, what didn't, calculating an approach speed that would be safe with the damaged wing. He flew the approach a few knots above stall. The margin was tiny. Too slow, and the wing stalls. Too fast, and the aircraft overruns the runway. He landed with approximately 100 meters of runway remaining. 0 injuries, 0 fatalities. The Australian Transport Safety Bureau's final report ran 344 pages. De Crespigny later said the only reason they had a chance was the fuel. They had enough of it to take time and think. We had fuel, and fuel gave us time. The engine that failed had a specific manufacturing defect. Rolls-Royce changed the specification for that oil feed pipe across the entire Trent 900 fleet. Every engine was inspected. Every airline grounded its A380s temporarily. It was the closest the A380 has ever come to a catastrophic loss in over 800,000 flights and 7.3 million block hours of operation. And the reason it wasn't catastrophic is precisely because of how the aircraft was designed. 4 engines, not 2. Triple redundant flight controls. Crew trained to operate with degraded systems. The aircraft kept flying. That's not luck, that's engineering. But there's one system we haven't talked about yet. The one running quietly underneath all of this, making constant invisible decisions. If you sit in the captain's seat of an A380, you'll notice something missing. There's no yoke, no mechanical control column running down from the ceiling. There's a small side stick to the captain's left, another to the co-pilot's right. That side stick doesn't move anything, it just sends an electrical signal. The A380 is a fly-by-wire aircraft, 4th generation. Every input the pilots make is routed through flight control computers that decide what the aircraft should actually do. The computers cross-check the input against the aircraft's current state. They check whether the input would exceed structural limits. They check whether it would stall the wing. Only then do they signal hydraulic actuators to move control surfaces. The pilots aren't flying the aircraft directly. They're requesting that the aircraft fly a certain way. The aircraft decides whether their request is reasonable. If you came up flying older jets, that sounds horrifying. If you came up flying Airbus, you know it's exactly why this works at 575 tons. But here's the system that fascinates engineers: the A380's fuel management and monitoring system. The aircraft has 11 fuel tanks, 5 in each wing, 1 in the horizontal stabilizer at the tail. The tanks are connected by 21 pumps and 46 control valves. The computers running this system are constantly moving fuel around the aircraft during flight. Why? Because the aircraft's center of gravity matters more than you'd think. Picture balancing a pencil on your fingertip. Hold the pencil with most of the weight forward. It's stable, but takes effort to keep it upright. Move the weight backward and it becomes nearly weightless on your finger. Move it too far back and the whole thing tips. The A380 in flight is balancing the same way. The wings provide lift. The horizontal tail at the back provides a downward force to keep the nose pitched correctly. The further forward the center of gravity, the more downward force the tail has to produce. That downward force is drag. Drag is fuel. So during cruise, the A380's fuel system pumps fuel from the main wing tanks rearward into the trim tank in the horizontal stabilizer. This moves the aircraft's center of gravity backward. Less downward force needed from the tail. Less drag, less fuel burned. The system is doing this constantly, in real time, with fuel quantity accuracy of plus or minus 1%. The probability of an erroneous but believable fuel reading is engineered to be less than 1 in a billion per flight hour. And remember those flexing wings from Act 2? After takeoff, the fuel system pumps fuel from inner wing tanks to outer wing tanks. The added weight at the wingtips pushes the wings back down, reducing the bending forces at the wing root. The fuel itself becomes a structural component. The wing and the fuel system are the same machine. There's one more system we have to mention, and it might be the strangest one. The A380 sits in its own wake turbulence category, the only aircraft on Earth assigned the ICAO super classification. No other passenger jet generates wingtip vortices this strong. Following aircraft have to maintain 7 to 10 nautical miles of separation. Air traffic controllers add the word super to all communications involving it. The vortices persist for over a minute behind the aircraft, kilometers long, strong enough to flip lighter jets. On January 7, 2017, a Bombardier Challenger 604 business jet was cruising over the Arabian Sea at 34,000 feet. An A380 passed 1,000 feet above it in the opposite direction. Both aircraft were exactly where air traffic control had cleared them to be. A minute later, the wake of that A380 caught up to the Challenger. The business jet rolled, completely upside down. Both engines flamed out. The aircraft dropped 9,000 feet through several rotations before the pilots regained control. 2 passengers were seriously injured. The aircraft was written off. The A380 wasn't doing anything wrong. The Challenger wasn't doing anything wrong. The A380's own wake, more than a minute and several kilometers after it had passed, destroyed another aircraft entirely. That is the price of holding 575 tons in the sky. In February 2019, Airbus announced the end of A380 production. The math hadn't worked. The aircraft cost roughly $25 billion to develop. Production cost per unit exceeded the sale price. Of the 251 passenger aircraft built, more than 120 went to a single airline. That airline is Emirates, and their president, Sir Tim Clark, refused to accept the obituary. In 2024, Emirates launched the largest aircraft refurbishment program in the history of commercial aviation. $3 billion to rebuild the interiors of 116 A380s. New first-class suites. New premium economy cabins. Rebuilt lounge bars, showers. At the IATA Summit in New Delhi in June 2025, Clark told reporters Emirates would operate the A380 into the late 2030s, possibly the early 2040s. When asked about an A380 with new engines, the much-discussed A380neo, he gave a rare honest answer. "I'm still shown the door when I mention it, but I'm still asking." Here's what Clark understands that most of the industry doesn't. The A380 was a bet on a future that didn't arrive. Aviation moved toward point-to-point routes flown by smaller, twin-engine aircraft. The 747, the A340, the A380 were the last generation of four-engine giants. But Emirates flies routes nothing else can do. Dubai to Sydney, Dubai to New York, 615 passengers in premium comfort, 15,000 kilometers non-stop. The Boeing 777X that was supposed to replace this kind of capacity is 6 years behind schedule. So the aircraft that was supposed to die in 2021 is now being rebuilt to fly another 15 years. That's how you keep a 575-ton aircraft in the sky. Not with one system, not with one breakthrough, with wings that bend on purpose, with a body that breathes, with 4 engines designed to fail safely, with computers that decide what the pilots actually meant, with fuel that rebalances itself every few seconds, and occasionally with 5 pilots, 50 alerts, and 100 meters of runway to spare. The A380 isn't proof that humans defeated gravity. It's proof that with engineering this precise, gravity becomes just another problem to negotiate with. So here's a question for the comments. Emirates is spending $3 billion to keep aircraft flying that Airbus stopped making because nobody else wanted them. At what point does loyalty to an extraordinary aircraft become an irrational business decision? Or has the A380 simply done its job too well to ever be replaced?